We start by defining a capacitor now. So what is a capacitor? Now capacitor consists of two conductors separated by a non-conductive region. So there are two conductors and they are separated by a non-conductive region. So what is the capacitance? So capacitance, which we denote by C, the capacitance of a capacitor is the ratio of magnitude of charge on either conductor to magnitude of potential difference between conductors. So say you have two conductors, the charge on the first one is plus Q, on the second one is minus Q, and the potential difference is delta V. So C is equal to Q over delta V. Now notice that capacitance is always a positive quantity and its units are charge is in coulomb, potential difference is in volts, so 1 coulomb per volt, and this you denote by 1 F or 1 Faraday. Now we talk about parallel plate capacitors. So electric field generated by a single plate which is positively charged, so this we have denoted before and computed it at the end of chapter 1. So if the area of the plate is say A, then the electric field is Q over 2 epsilon 0 A. Now if there are two plates and these plates are of opposite charge, then this electric field doubles because one field is attracting the electric field, so it doubles. So you get electric field as Q over epsilon 0 A. Now the magnitude of potential difference between these plates, this is equal to, we use our formula for potential difference, E vector dot dx vector, and you move from initial distance 0 to final distance d. So you move from one plate to another because electric field comes out from plus Q and goes into minus Q. So theta is 0 between electric field and the displacement. You can see electric field is in this direction and so is the distance or the displacement. So you can take this as E dx. It will be E dx cos theta. Theta is 0, so cos 0 would be 1, and therefore you get delta V as E times D. So capacitance is given as Q over delta V. This is our formula. So you can write it as Q over E times D. Now E we have talked about between two plates is Q over epsilon 0 times A. So Q cancels out. So capacitance is given as epsilon 0 A divided by D. So the first thing is, as area increases, capacitance also increases. Number two is, as distance decreases, as distance becomes small and small, the capacitance increases. Now we talk about dielectrics. Now dielectric is nothing but a non-conducting material. So this could be a glass or a rubber, and it is placed between the two plates of the capacitor. So the original capacitor looks like this. There is nothing between the plates, only air. And instead of air, now you put something else. So maybe you can put in glass or rubber or some other non-conductive material. So dielectric is a non-conducting material that could be glass or rubber or something else. Now this dielectric will increase the capacitance. So now C1 would be kappa times C, and this kappa is called the dielectric constant. So this dielectric constant is always greater than 1. When it is 1, you call there is no dielectric, it is just air. So for a parallel plate capacitor, if you have a dielectric, then the capacitance becomes kappa times epsilon 0 A over D. So we have modified the formula for the single capacitor by introducing a dielectric in it. So there is nothing in it except multiplication by the dielectric constant kappa.